So the last feature we'll talk about is the coordination mechanisms that are provided with the built-in monitor objects in Java, and they're the ones that allow threads to wait and notify each other so that the operations occur at the right order, at the right time, at the right place, and so on. So as we saw, the Java synchronized methods and the synchronized statements only allow you these partial solutions to the concurrency challenges we talked about. And so therefore, monitor objects give you some other stuff, the coordination features. There's several of these methods. They are very simple, but perhaps simplistic, as we'll see. But they do solve simple use cases reasonably well. So there's three general categories of methods: wait, notify, and notifyAll. And there's a little variant here and there we'll talk about. So the wait method causes the current thread to be suspended, to block, until another thread invokes the notify or notifyAll method on the same object. So wait is actually very similar to await on a condition object. Notify wakes up a single thread that's waiting on the object's monitor. So if somebody's called wait, then notify will wake one of those threads up. If multiple things call wait, then one of them will be awakened. And, surprise, surprise, notifyAll wakes everybody up who's waiting on the object's monitor. So those are the three main methods. The trick with notifyAll, as with signalAll, with condition object, is it can lead to the thundering herd problem, where lots of threads wake up, all descend on the monitor object, all try to contend for its single intrinsic lock, its single monitor lock, and then they'll all sort of have to go back to sleep very quickly. So thundering herd is a problem with notifyAll. Here's typically the way you would do this. You have to remember that monitor objects have a single entrance queue and a single wait queue. So they have a single intrinsic lock. That's what the entrance queue is related to, and a single wait queue, which is what the intrinsic condition relates to. It just only got one. And the entrance queue is used to serialize access into the critical section. And the wait queue is where waiting threads are parked until they're notified they can make progress, until the conditions have changed so they may be able to make forward progress. All methods on an object related to notify, notifyAll always work on the one and only wait queue associated with that particular object. And therein lies the problem. There's only one wait queue. So let's take a look at a simple example here. This is a new implementation called Simple Blocking Bounded Queue. And it has put and take methods. And you can see here that what we do is we go ahead and first we get a synchronized lock on this particular object using the intrinsic lock. And then while the list is full, we wait. So what will happen here is that wait will go ahead and put this thread to sleep and release the synchronized lock on this until someone comes along and calls take. So remember, wait will atomically do those two things. It releases the intrinsic lock and sleeps on the wait queue. You'll also notice that after we have put something in the queue, we have to notify all the other threads that it may be possible for someone to take things out. And this is a really bizarre kind of a botch due to the oversimplicity of the underlying single wait queue in a monitor object, is that you end up having to call notify all over the place, which leads to the thundering herd problem. And the reason for this we'll talk about shortly. It's because the waiters are non-uniform. When things are waiting, they can be waiting for it to be is full. They can also be waiting for it to be is empty, and we'll talk more about that later. So this notifyAll is required for things like this, and that's because built-in Java monitor objects only have one wait queue. If you think back, by the way, to our discussion earlier about condition object, when we talked about how array blocking queue was implemented, you recall it had two condition objects, not empty and not full. And therefore, it was able to have what was called uniform waiters, because everybody who wanted to wait for the queue to be not empty waited on the not empty condition. Likewise, all the threads that wanted to wait for the queue to be not full waited on the not full condition. But with the built-in monitor object is only one wait queue, so we end up having to call notifyAll a lot more. Likewise, when take calls wait and the queue is empty, that's the guarded suspension pattern again. So while the list is empty, we wait, which atomically releases the lock and sleeps on the wait queue. And again, when we finally take something out of the queue, we have to notify everybody that excuse me, the queue may no longer be full because we just took something out of it. And again, waiters are non-uniform because we're waiting on is full and we're waiting on it is empty on the same monitor condition. Big limitation with Java. We'll talk about put and take here shortly. This stuff is implemented under the hood using POSIX-like synchronizers. POSIX is the portable operating system standard interface for Unix and Linux-like systems. And there's something called the POSIX reentrant locks or POSIX mutexes, mutual exclusion locks, and they can have reentrant semantics. And so you can think of an entrance queue as basically like a POSIX recursive mutex. That's typically how they're implemented under the hood. And you can think about wait queues as being equivalent to POSIX condition variables, which is also how they're typically implemented under the hood. And it's beyond the scope of this discussion to go into that in detail, but just be aware that most Java implementations use low-level C or C++-like APIs to do the locking for the built-in monitor object synchronizers. These are similar to condition objects, but they're written in a lower level. They use the lower-level locking primitives. And if you want to make your head explode, take a look at some of the implementation stuff, and you can see how it's all done in the out-of-the-box Oracle implementation of Java. OK, so that was a quick overview of the coordination methods. We're about to talk in more detail and show examples of how they work in practice.